left-handed versus right-handedness in a molecule. So when we look at these, there are mirror images. Mirror image is really a test of that. Is there a mirror image, and are they superimposable? If they're not superimposable, they're different molecules. This might not seem like a huge issue to you guys, like why would that possibly matter? But when we get into other topics like enzymes, enzymes are huge proteins, generally huge proteins that have sites where things can attach. So for instance, we might have some protein that has receptor sites on it for like green and yellow and blue, and this would fit in there, right? And that would fit in there and work. Whereas this molecule, it can't happen, right? There's no way we can get all three of those in the right place. So this seems like a minor issue to you guys, like they're so similar, like how could it possibly make a difference? But that does make a difference. So this, these stereoisomers or enantiomers can make a huge difference. Chemistry usually, but in biology. You're probably familiar with Louis Pasteur. Came up with pasteurization, named after him. Also came up with the first vaccine, I believe, for rabies. I think that's true. But he was the first one to discover this. And apparently he could tell the difference. Well, we'll come back to that in a minute. We'll get to next. So we designate these as D or L. Did I get this far with you guys? Yes. Okay, so it's D or L. I can get that for the other class. Oh yeah, we did do some of this. So we look at this one as an example. I know we did this before, but we start with the double bonded O as far as the top as we can. It's an aldehyde. It's going to be at the top. There's a ketone. You want it as close as you can. It's in the middle. That's the way it be. But and we work our way down. We look at the asymmetric carbon. This is the only asymmetric carbon. That makes it the last. If we look at the OH, the way it's drawn to the left tells us this is the L form of this molecule. If we switch those two things, we would have the D form. Here we've got two carbons. The last one, this one, is to the right. That was to the right also, of course, but since that's to the right, that's our D form. Did I say that was a D? That's the L. Yeah, I said that right? Okay. This one, even though I tried to maybe trick you, is not a D or L, because that's not an asymmetric carbon. It's just two H's. Probably not even a sugar. That's not a sugar. Not that sugars are the only molecules that have D or L, by the way, but we're studying that. We can tell how many stereoisomers there are by using the formula. It's 2 to the n, where n equals the number of chiral carbons. That's not a super useful little math thing, but it does give you an idea of how many answers there are if I ask you to draw all of these possible stereoisomers. So if we look at this example up here, there is only one carbon, so it's 2 to the 1. There are two possibilities, right? We can have the OH on the left, or we have the OH on the right. That's our only two choices. On this one, it would be 2 to the second power, because there's two chiral carbons. We have four choices. Here's one of them, right? OH to the right, OH to the right. We have OH right, OH left. We have OH left, OH left, and we have OH left, OH right. All those possible combinations of having those two OHs on the left and the right. We had 3 asymmetric carbons, right? It would be 2 to the third, it would be 8. All right? So you can calculate that. You need to understand how to determine whether the carbon's chiral or not, and then you just plug those numbers in. They don't have to be next to each other, by the way. We got something in between there. You still have two chiral carbons split apart. So how many stereoisomers do we have for this one? Well, I've already showed, kind of given you part of the answer here, because we have 4 chiral carbons that I put in red. So it's 2 to the 4th, so we have 16. Right to the 4th, 2 times 2, 4 times 2, 8, yes. All right. Now you guys probably don't want to draw all those molecules like that, right? That's a lot of writing, a lot of H's and OH's. So we have some shortcuts we're going to be using. Remember, these are three-dimensional, and that gets a little bit difficult. I mentioned this before, but you guys are going to have a little bit of trouble with three-dimensional models because they're not just a straight chain. So when you look at them, you have to look at it in a certain way, which we'll come back to here again before we're done here in a few minutes. So we write the primary function group at the top. That's the aldehyde. If it's a ketone, we still can use that triangle, but the triangle will be somewhere in our line, in our lineup. Okay, but we start with our aldehyde group on top. So this is representing the aldehyde group, the triangle. We write this vertically, we don't worry about the zigzagging this, and we write our OHs or our H's, right? This is implied as an H for where they're at. In this case, I'm showing them all to the right. And here's the shorthand form of that, where we just don't even show the H's at all. We just know there's an H attached here. So these lines are representing where the OH's are. So it goes aldehyde, right, and then down here, this circle represents our C2 or CH2OH. Okay, so our little triangle represents this. I think this is more carbons than I want to have down there, but we have our carbons of the OHs, just the lines to show which way the OHs are, and then we have a circle to represent this carbon. I guess I've got them all. Yeah, 1, 2, 3, 4, 5, 6 carbons on those. Okay. If you're trying to draw that from a model, this is what I showed you this last time somewhat, but you start up here, right? This is going to be our first carbon. That's going to be your triangle. And then, in order to look at this, you have to keep rearranging this. You have to have this H and the OHs on the carbon sticking out, jutting out towards you. That's how you determine if it's to the right or the left. When you look at it that way, it's to the right. When I'm looking at it, it's to the left, but that doesn't count. I have to look at it the correct way. I have to have these coming out at me. Okay, so it's not arbitrary. You can't just write left or right on a model, build a model in an arbitrary way. Now, if you can do this, you can kind of make them all sticking out at you, and you'll notice that what happens when you do that is the whole molecule just kind of curls around and really almost makes a ring. Okay, but then you can see, here's my first carbon with a double bond O, the aldehyde carbon. There's the second carbon, OH to the right. Third carbon, OH to the right. Fourth carbon, OH to the left. Fifth carbon, OH to the left. And then our last carbon is not the chiral carbon, our CH2OH, represented by the circle. Okay, so we have a left, left, right, right. So we're trying to draw that with a Fisher projection. The molecule I'm holding. Our last asymmetric carbon, our four asymmetric carbons, has us to the right. So this is a D form of whatever molecule this is. Okay. All right. So this is number 3 is what I'm saying. You can take that whole thing and kind of wrap it around so they're all pointing out at you. You don't have to do that. You just keep moving it around and going back and forth too. So, and then we put our H's, our OH's. We don't even know we put the OH's. We just use the lines for the OH's. All right, so we're going to talk a little bit about name, but more about classification. We can classify sugars and carbohydrates in many, many ways. 7 of them, what I've got here. They can have an aldehyde, and we call them aldoses, right? That's not a name, that's a category. It's a category. Most of the sugars we're going to study are aldoses. The most important ones are aldoses. They can be ketoses also. Instead of an aldehyde group, you might have a ketone group. There's really only one that's important to us. You've probably heard of it, fructose, fruit sugar. But it is a very important one because it also happens to be table sugar. So it's a very common and abundant sugar, this one ketose. We can also classify them by how many carbons. Right? Our smallest ones are trioses, tetroses, pentoses. Hexoses are quite common. Pentoses are pretty common. Ribose and deoxyribose, where are those found? Yeah, RNA and DNA, right? So that's the sugar, those are pentoses. So they're pretty important sugars. We don't study them a whole lot in this unit, but they are important because they're DNA and RNA. But the hexoses tend to be going to the most common for us that we're going to study. Sometimes we can combine these first two categories in their classification, or we can call them aldohexose, meaning it's an aldehyde with 6 carbons. Ketopentose, a ketone with 5 carbons. Right, so we combine a couple of these categories. And then, as I just mentioned, I just showed you this idea, we can determine if there are D or L forms of a particular sugar. Okay, and that's by looking at the last asymmetric carbon. Right, so that's another one you're going to see a lot. This one, we're going to skip over a little bit for now, but you've probably heard these terms before. I find that students don't know what they mean so well, generally, but we've got monosaccharide, disaccharide, polysaccharide. The difficulty is knowing what the units are, but you'll figure that out as we work through this in the next couple of classes. Once you figure out what a monosaccharide unit looks like, well, you put 2 together to get a disaccharide, you put more than 2 together to get a polysaccharide. So right now, you don't know how to do that yet. We also have, well, I check the links, but we also have something called optical activity. This is actually what Ludwig Pasteur did. He took a pile of crystals of a particular chemical, tartaric acid, and shone a light through them, and you could see that it rotated the light one way or the other. And he made 2 piles out of these crystals. Now this sounds a lot like D or L, right? Because there's a D or an L in it. But we use positive and negative to represent these rather than D or L. What do you guys know about polarized light, or polarized lenses, say, for sunglasses? Yeah.
It only lets one direction of the wave.
Ah, yeah. How does light travel?
It's two waves, one goes up and down, one goes side.
Well, yeah, we can have waves of any direction, really, right? We can have waves that are in this direction or this direction. Yeah. So they're coming at you. It's a whole mixture of these. And if you have polarizing lenses, essentially, it's like a Venetian blind, right? It only lets certain wavelengths through. So if your lens is like this, the wavelengths that go this way can get through, but not the ones that go this way, right? They get blocked. So it's blocking a lot of the light that's getting through, certain wavelengths, certain directions of the wavelengths. So if we have 2 polarizing lenses, right, and we have them like this, and we turn them, now we don't let any light through. Okay? Do this with your expensive polarizing glasses. Break them in 2. So you take one lens and do that, turn it, and you can block all the light. And then you get new glasses. So let's watch a little video about something that is related to sugar and this.
In this beaker we have some distilled water, we want to examine optical properties of both liquids between 2 pieces of polarizing films. The first piece has been placed on top of this light box, and now I will place the second piece on top of this ring. And what we will do is rotate the top piece.
All right,
We see
all right,
that
he's
no
done
light
this, so it lines like this, it's changing.
Rotate back, we see the light
Comes back.
coming through.
All right,
Now I will take the beaker that has the water in it and place it between these two pieces of polarizing films. What we will do next is rotate the top polarizer, and we see that the light comes through only when the polarizers are parallel to each other.
all right, the water has no effect.
The beaker of water with the beaker that has the sugar solution in it, and we will rotate 90 degrees, and we see color changes occurring. These changes are due to the optical activity of the sugar solution that is present in Caro's syrup.
Oh, is that because it's polarizing?
So it's changing the direction of the polarized light as it passes through the sugar solution. So right now, right, he has the two polarizing films lined up like this. So most of the light just comes through. But as it passes through the sugar, the light is rotating 90 degrees, either to the right or to the left, but it's 90 degrees, so now it's no longer getting through the syrup. Okay? It's as if our polarizing films were 90 degrees. They're not really 90 degrees, but the light is changing as it passes through the sugar to where, even though these are lined up, it gets through the first one, passes through the sugar, can't get through the second one. Okay? When he turns it, the upper polarizing film, now the light around the beaker can't get through anymore. However, the sugar is rotating the light. So the sugar, while the light gets through the first polarizing film, is rotated through the sugar and gets through the second one. And then it shouldn't. Okay, so pretty bizarre phenomena. I can't say I know much more about it than this, but I think I'll show this one more time. Okay, so now the light's not getting through normally, but it is passing through the sugar solution. All right. I wouldn't say this is a super important aspect for us, but yeah.
Is that just diffraction? Like light is passing from one medium to another? Because I'm wondering about the color change too. So it's just like a range of diffraction, and as you're sliding the...
Yeah, I don't think so. I mean, diffraction may be the color, perhaps.
Yeah.
Like a little purple.
Uh-huh.
But I'm assuming that's the plane of the light.
Yeah. Weird.
All right, so Pasteur discovered this. Here's what's a little bit difficult. This activity is related to DRL, but dextrorotatory doesn't always go with D. Okay, and levorotatory doesn't always go with L. So in some cases, some substances, the D form is levorotatory, and then the L is always the opposite of whatever D is. So if D is levo, then L is dextro. If D is dextro, L is levo. Yeah, I don't look at Facebook very often.
That's like
I don't know who Cindy K. Reed is. All right. The way to turn that off, that's been happening a lot lately.
if you don't have any friends, like another notification.
No, I don't want any friends. All right. So, I don't think some of you weren't listening very well to this, but whatever D is in terms of its optical activity, L is always the opposite.